Kriti Goel from Indian Institute of Technology, Bombay. She will speak on characterization of F-rational rings using tight Hilbert polynomial. Kriti, please.
Thank you. Hello, everyone. Thanks for joining in. I'm Kriti Goel from IIT Bombay. And firstly, I hope everyone is safe and sound. And I would like to thank the organizers for giving me this opportunity to talk, and also for organizing this conference in these difficult times so that we can learn more mathematics. I'll be talking about characterization of F-rational rings using the tight Hilbert polynomial. And it's a joint work with Vivek Mukundan and Jugal Verma. So let's begin with some notations and definitions. So for us, R will be an I will be an M-primary ideal. So given a sequence of ideals I sub n, we say it is an I filtration if it satisfies the following three properties. Firstly, it should be a descending sequence of ideals. Secondly, it should satisfy the grading property. And finally, it should satisfy the property that the nth bar of the ideal I should be contained in I sub n. Moreover, if an I filtration satisfies this property, that there exists a natural number k such that I sub n is contained in n minus kth part of the ideal, the filtration is said to be admissible filtration. So what is a very common example of an admissible filtration is looking at an I-adic filtration. This means given an ideal M primary ideal I, we look at the nth bar, the sequence or the set of ideals which consist of nth bar of the ideal I. Now the other interesting or most sought after filtration, which is admissible, is an integral closure filtration. Let me quickly define what it is. So an ideal I is said to be, given an ideal I, the integral closure of I, which we denote by I bar, is a set which consists of all those elements X in the ring, satisfying an equation of the particular form, where these coefficients come from the corresponding powers of the ideal I. So if we consider the collection of the integral closure of powers of the given ideal I, this forms an admissible filtration if the ring is analytically unramified. So this characterization was given by David Rees. Let me recall here, by analytically unramified, we mean that the M-adic completion of the ring is reduced. What he proved was the following. He said that a ring is analytically unramified local ring if and only if the collection IN bar is an I-admissible filtration, and this is true for any M primary ideal I. So what properties do admissible filtrations have that we can use? So associated to an I-admissible filtration F, let's say suppose the dimension of the ring is T, we associate a length function to this filtration, which we call as the Hilbert-Samuel function of the filtration F. This is precisely length of R over I sub n. And it is popularly known that this length function is actually a polynomial function. This means that there exists a polynomial with rational coefficients of degree t. We call this polynomial as the Hilbert-Samuel polynomial of the filtration, and this means that the function and the polynomial coincide for large enough values. So this was a general introduction, but then we want to target a specific closure operation in characteristic P, which we call as the tight closure operation, and further study it. So let me recall the definition of tight closure. So as I mentioned, we'll be dealing in characteristic P. The ring is a Noetherian ring. By Q, we mean the prime power. So Q is P to the E, where E is a natural number. So if we have an R ideal I, by I bracket Q, we mean the eth Frobenius power of I, and it is the ideal generated by A to the Q, where A varies over all the elements of the ideal I. One more notation, by RO, we mean the complement of union of all minimal prime ideals of the ring R. And in this setup, the tight closure of the ideal I is defined as a collection of all those elements in the ring, such that there exists a C in RO, such that C times x to the Q is in the eth Frobenius power of the ideal, and this should hold for all large Q. Moreover, if I is equal to I star, then the ideal I is said to be tightly closed. Next is a very interesting containment relation. So we studied the tight closure. We looked at the tight closure. We looked at the integral closure of the ideal. And this is an interesting containment relation, which is true for these closure operations. I is always contained in its tight closure, which is further contained in its integral closure. So a very quick example of tightly closed ideals is integrally closed ideals. This means if an ideal I is equal to its integral closure, then it's also equal to its tight closure. Other trivial examples or quick examples using this observation is when the ring is a regular local ring. In this case, if you pick any ideal, it's tightly closed. This requires flatness of Frobenius functors and various other things. The other example is a consequence of Price-Korsakov theorem. And it says that if we have a principal ideal, then the tight closure and the integral closure of the ideal coincide. So now once we have defined the closure operation, what we want to do next is the following. We want to look at the tight closure of the power of the M primary ideal I, and then see under what conditions it is an admissible filtration, and then proceed further. So we actually figure out that under certain circumstances, it is indeed an admissible filtration. So what are the assumptions under which this happens is the following. So the ring is a D-dimensional, analytically unramified local ring with prime characteristic P. I is an M primary ideal, and T is a collection of tight closures of the powers of ideal I. Then in this case, we prove that T is an admissible filtration. This means when we look at the tight Hilbert function, which is length of R over IN star, it is a polynomial function of degree D with rational coefficients. We call it as the tight Hilbert polynomial. We call it as the tight Hilbert polynomial. And if the expression of the tight Hilbert polynomial is written in this particular form as a linear combination of the binomials, then the leading coefficient is called the multiplicity of the ideal. And of course, all the other coefficients are called the tight Hilbert coefficients of the ideal I. And the coefficient we'll be interested in looking at the stock is even star of I, which I'll explain later. But the next thing I would like to define and shift focus to are F rational rings, because these are the rings we want to characterize using these coefficients. So let me quickly define what F rational rings are. So again, a ring is Noetherian. It has prime characteristic P. We say an ideal I is of principal class if it is generated by height I number of elements. And in this particular setup, the ring is said to be F rational if ideals of principal class are tightly closed. Now, these F rational rings also have certain interesting properties. These properties help in characterization of F rational rings, and also, of course, they help in building up more examples and in checking various examples. I'll just mention a few properties here to give you a feel of F rational rings. So we assume R is either a locally excellent ring or it is a homomorphic image of a Cohen-Macaulay ring. In this case, the ring is F rational if and only if it is equidimensional and there exists a parameter ideal which is tightly closed. What is interesting to observe here that we only need to check for one particular parameter ideal. As a quick corollary, one can also see that if R is a Cohen-Macaulay ring to begin with, then it is F rational if and only if there exists one parameter ideal which is tightly closed. This means it's enough to check just one to see if it is F rational or not. The other characterization is when its localization at every maximal ideal is F rational. So let me mention here, we have not assumed Cohen-Macaulay localness over here, but let's say if we have a local ring and we have a non-zero divisor X in the maximal ideal, such that the quotient ring is an F rational ring, then the ring will be F rational. Unfortunately, the converse of this statement is not true. This means that R being F rational will not say that the quotient R mod XR for a non-zero divisor X is F rational. This and a few more examples I'll illustrate next. So the first one is quotient of the polynomial ring Kxyz by the element x square minus y cube minus z to the 7. K is a field and it has a prime characteristic P. We pick an ideal I, which is ideal generated by y comma z. Now observe here that this ring is a Cohen-Macaulay ring. The ideal I is a parameter ideal. And of course, small y and z are images of capital Y and z in the ring R. So in order to check this ring is F rational or not, it's enough to check that the ideal I is tightly closed or not. And one can easily check that the element X, which is not an element of I, is in the tight closure of the ideal. And since it's a parameter ideal, we get I is not tightly closed, and hence the ring is not F rational. So while it might seem easy to check whether a ring is F rational or not, this might be an example in disguise, because even a same ring with different characteristic might behave differently. And this is what the next example illustrates. So we have a quotient of a polynomial ring, kxyz by x square minus y cube minus z5. K is a field, and again, I is the ideal generated by y comma z. Small y and z denote the images of capital Y and z in the ring R. Again, in order to check the ring is F rational or not, we just need to check if I is tightly closed or not. So these two examples I've picked up from Brunson-Herzog, chapter 10. If you're interested in looking at the details, please, you can go back to the book and see the details. Example 2 requires some work, and this is what it's proved over there. They prove that X is not in tight closure if and only if the characteristic of the base field K is strictly bigger than 7. So this computation is characteristic dependent. In particular, it is proved that the ring is F rational if and only if the characteristic is at least 7. Okay, so this was the background details of it. Let's come to the main topic. We want to characterize F rational rings using even star of I. But why even star of I? So this coefficient is what is called as the Chern number of filtration, and this is not the first time that people have looked at the coefficient and used it to characterize rings. This has happened in the past. Of course, there's a good amount of literature and history of results where people use vanishing or bounds on these coefficients to study or to characterize rings. So I'll quickly recall here. If we have an admissible filtration, and we have Hilbert-Samuel polynomial P sub f of x, and we have the following expression, then the coefficient E sub 1 of f is called the Chern number of the filtration. And as I mentioned, there are some results in the history which I would like to quote here. The first one is by Giese and few more people in 2010. They characterize Cohen-Macaulayness of a ring using the vanishing of even Q for some parameter ideal Q, provided that the ring is unmixed. In the same year, Goto and Ozeki proved that the ring is Buchsbaum local ring if and only if it is unmixed and even Q is constant, and also it is independent of choice of parameter ideal Q and R. So before I proceed to the main theorem, there are small results and lemmas which we'll use in the main theorem, and of course they are interesting their own individual respect as well. I'll quickly quote them and then proceed towards the main theorem. So this is what is called as the intersection theorem for tight closure. So a version of this theorem for integral closure, and of course a motivation for this theorem, comes from a result of independent result of Huneke and Ito, where they proved this result for integral closure filtration. Prime characteristic P, I is ideal generated by regular sequence. We proved that for all n bigger than or equal to 1, the following intersection condition holds. And as a consequence, we have this theorem by Watanabe, suggested to us by Watanabe. And it says that, of course, under the above restrictions, that we have a Noetherian ring, prime characteristic P, ideal I generated by regular sequence, then the ideal I being tightly closed implies that all its powers are also tightly closed. So we use these two results and prove the main theorem, which is as follows. So we assume that Rm is analytically unramified Cohen-Macaulay local ring, prime characteristic P. Then the ring is F rational if and only if even star of I vanishes for some parameter ideal I. I would like to emphasize here that we only need to check it for one particular parameter ideal I. Since it's a very short proof, I'll quickly give the proof. So let's
Uh,
look at, yes, sir.
so we have very 1 minute, I think you can take at most.
Yes, sir, it's about a minute. Yeah, thanks. So let's look at the forward part. Let R be F rational and we pick a parameter ideal I. We need to show that even star of I vanishes. But by definition, I being parameter ideal and R being F rational will imply that the ideal I is tightly closed. And by the previous slide, the result of Watanabe, we get not just I, but all the powers of I are also tightly closed. This means when we look at the tight Hilbert polynomial of the ideal, it coincides with its Hilbert-Samuel polynomial, and this will say further that the coefficient even of I, which in this case is even star of I, vanishes. So this is the forward part. For the backward part, let's say we have a parameter ideal I such that even star of I is 0. We need to prove that the ring is F rational. So in order to prove this part, we look at what is called as the Northcott inequality. This was proved for filtration by Hakaba and Marley, and this is the following inequality. In our case, even star of I is 0. E0 star of I is the multiplicity of the ideal. Since the ring is Cohen-Macaulay and I is a parameter ideal, E0 star of I is precisely length of R over I, which gives us the left side inequality. Since I is contained in I star, we have the right side inequality. These two combined say that length of R over I is same as length of R over I star, and hence these two ideals are equal. So now we have a ring which is Cohen-Macaulay. We have a parameter ideal which is tightly closed. This will say that the ring is F rational. So this completes the proof of characterization. These are references, and thank you. Yeah,
Okay,
I'm
thank you
open
so
for questions.
thank you so much.